Section of the table, we are going to focus on doing tests or using contingency tables. This says 11.2, but it's really 11.3 in the book. So, first of all, let me change that up here. Change to 3. When data is tabulated in table form in terms of frequencies, several types of hypotheses can be tested by using the chi-squared test. The test of independence of variables is used to determine whether two variables are independent of or related to each other when a single sample is selected. The test for homogeneity of proportions is used to determine whether the proportions for a variable are equal when several examples are selected from different populations. So we got a test for independence. Two variables are independent of each other. And the other one is homogeneity, determine whether proportions for a variable are equal when several samples are selected. So let's say, test for independence. The chi-squared goodness of fit test can be used to test for independence of two variables. The hypotheses are as follows. There is no relationship between the two variables. There is a relationship between the two variables. Not too hard of a hypothesis. If the null hypothesis is rejected, there is some relationship between the variables. Test for independence. In order to test the null hypothesis, one must compute the expected frequencies assuming the null hypothesis is true. When data are arranged in table form, the independence test, the table is called a contingency table. So we're going to make some contingency tables. So it looks like this. You got row 1, you got column 1, so down the line. The degrees of freedom for a contingency table is rows minus 1, columns minus 1, which is R minus 1, C minus 1. And we'll show an example of that. And our test value is the same thing. That doesn't change except for our degrees of freedom. And our expected frequencies change. Notice our expected now is rows times sum times column sum divided by grand total. So let's try one. A sociologist wishes to see whether the number of years a college person has completed is related to his or her place of residency. A sample of 88 people is selected and is classified as shown. Alpha 0.05. Can a sociologist conclude that the person's location is dependent on the number of years of college? So here's the thing. Number going to college, 4-year degree, advanced degree, urban, suburban, rural, total. 88 people. The hypotheses. A person's place of residency is independent of the number of years of completed college. A person's place of residency is dependent on the number of years of place of college. So the first thing we're going to do is find our critical value. Rows minus columns, rows and minus columns. So if we're going to go back to this table, we had 1, 2, 3 rows, 3 columns, 3 rows. Oops, too far back. We'll come back to this one for a second. We're going to compute the expected values. Yeah, they're off on their rows and columns in this critical value. They say the critical value is 4.605. If we go back to our formula here on this chart, I'm just going to go back a few pages here. It says our expected value is number of rows minus 1, number of columns minus 1. So if I looked at this table, number of rows is 1, 2, 3 rows, number of columns is 1, 2, 3. So it should be 2 and 2, which is 4. I have to get my table here. 4 degrees of freedom. And it's because it's 3 minus 1 and 3 minus 1. It's be 4 degrees of freedom at 0.0. I can't remember what the alpha was. 0.05. 4 degrees of freedom should have a critical value of 9.488. So I'm going to change my critical value on this one. This should be 9.488 because the rows and columns. Unless I messed up, we'll come back and look at another example like this. So the expected value is row times sum, row, column, and then divided by grand total. So we have row, like in this one here, this is 1, 1, 35, Let me erase this here. 35 times 29 divided by my total 88. That's going to get my expected value. So like on this one, it's going to be 35 times 35 divided by 88 gives me that one. And the ones in the parentheses are my expected values. Now remember, our critical value was off a little bit. Now we're going to compute the test value. Now the test value gets to be very long, but it's nothing different than what we're doing. So it's 15 minus 11.53 squared divided by the expected. 12 minus 13.92 divided by expected. 8 minus 9.5 divided by expected. And we add all these up. So when we did this on this one, we ended up with our test value to be 3.01. So we're going to make our decision. Now, 3.01 is less than 9.488. Now they have the right critical value now. And so therefore, there is not enough evidence to support the claim that the person's place of residency is dependent on the number of years of college completed. Now, if I go back, since there's not enough evidence to support the claim, let's look at the hypothesis again. The claim was the person's residence is dependent on the number of years of college. So we did not reject, so it's independent. We're assuming that there's no relationship between the two. There's not enough evidence to support the claim that the person's place of residency is dependent on the number of years of college completed. Let's try another one. A researcher wishes to determine whether there is a relationship between the gender of an individual and the amount of alcohol consumed. A sample of 68 people is selected and the following data is obtained. At alpha 0.10, can the researcher conclude the assumption is related to gender? Hypotheses. The amount of alcohol that a person consumes is independent of the individual's gender. The amount of alcohol that a person consumes is dependent on the individual's gender is the claim. Critical value. Now this one's a critical value. I think they got the two critical values mixed up. We have 2 rows and 3 columns, so the critical value should be 2. So this one's a little off here. This one should be 2 degrees of freedom. 2 degrees of freedom at 0.10 should be 4.605. So this one's a little bit off here. So now, computing our test values, expected values. Computing our expected values. So we have our values here. We're going to take 27 times 23. 27 times 23 divided by 68, got 9.13. So when we look at our expected values, this is what we're going to get. Taking a row times our column divided by total. Row times column divided by total. And then up here, whoops. And we get all our expected values. Now, when we go through here, we're going to compute our test value. 10 minus 9.13 squared divided by 9.13. So on down the line, getting all our values subtracted out, we get a test of 0.283. So we have to make our decision. Notice that 2.83 is less than 4.165, so therefore there is not enough evidence to support the claim that the amount of alcohol a person consumes is dependent on the individual's gender. So the individual's gender does not determine how much alcohol they claim they drink. Now the test for homogeneity of proportions, which is the last thing we're going to talk about, is used when samples are selected from several different populations and the researcher is interested in determining whether the proportions of elements that have a common characteristic are the same for each population. So the hypotheses are the proportions are the same, and the other one is at least one proportion is different than the others. When the null hypothesis is rejected, it can be assumed that the proportions are not equal. The assumption of homogeneity of proportions is that the data are obtained from a random sample, and the expected frequency of each category must be 5 or more. So, not much difference in the values here. Researchers selected 100 passengers from each three airlines and asked them if the airline had lost their luggage on the last flight. The data is shown in the table. At alpha 0.05, tested claim that the proportion of passengers from each airline who lost luggage on the flight is the same for each airline. So the proportions are the same, at least one being different. Critical value. There is 3 columns, 2 rows, so 3 times minus 2, we get 2 degrees of freedom at 0.05. I think it was 0.05. 5.991 is our critical value. Compute our expected values. Same as before, how we compute these. We take it and go row times column divided by total, 7. What's nice about these is it should end up being the same if the proportions are the same. So then we had to compute our test value. 10 minus 7 divided by 7. 7 minus 7 squared divided by 7. So on the line, add them all up and we get our test value at 2.765. Now we have to make our decision. Do not reject the null hypotheses. 2.765 is less than 5.991, so there is no value there, so therefore there is not enough evidence to reject the claim that the proportions are equal. Hence, it seems that there is no difference in the proportions of luggage lost by each airline.